All right, guys, we're going to go ahead and go through how to wrap up this lab. So what we should have at this point is sheet 1, which should have all your launches, your angles, and then your heights. So what we have to do next is we need to calculate the potential energy of each shot. And to do this, what we're going to look at is the sort of calculation for the potential energy of each shot. The potential energy is going to be, so the formula is mg delta h. So since the ball is in the pendulum, for the mass, we're going to need to add the mass of the ball to the mass of the pendulum. So the pendulum itself is 35 grams. And for the brass, steel, and aluminum shots, for each mass, we're just going to add the mass of each shot to the pendulum. So for brass, that's 8.5 grams, giving us a total of 43.5. For steel, that's 8.3, and then aluminum is 2.8. So that gets us our 3 masses. And because it would be very tedious to do all of our math by hand to calculate these, I'm going to show you how to use Excel to kind of do the work for you. So the 3 formulas that we're going to need to do are 43.5 times 9.8 times the height, and then 43.3 and 37.8 times the height. So if we go back to our sheet, what we can do is make another sheet, and this is going to calculate our potential energies. So what I did was I went to sheet 1, I started with brass, I highlighted this data, copied and pasted it into this sheet. So this is a new sheet. You'll have to make this one if you want to do the math in Excel. So here are your heights, and I copied over the brass, the steel, and the aluminum. Now we want Excel to do some math. So the way that we do that is we click the cell that we want to do the math in, and we start with an equal sign. So you have to start with the equal sign to tell Excel that you want to do math. And then here's how we would type this in. So 43.5 is the mass of that we want here. Then we make the asterisk sign, and that tells Excel you want to do some multiplication. Then we do 9.8, asterisk again, and then we want to select the cell that has the height in question, and we can do that either by typing in the kind of location of that cell. So A2, we could do that, or we can just click the cell that we want to do the math on. So what this will do is Excel will take 43.5 times 9.8 times that cell, and then we click enter and it does the math for us. We want to extend this formula to all the other heights. So we go down to the bottom corner of that cell, drag down, and then that's going to do all the calculations for us, which is awesome. So this will be equals 43.3 times 9.8 times that height, hit enter, bring that down. And then, we need to do the same thing over here. So equals, this is 37.8 times 9.8 times this height, hit enter, and then drag this down. So once we've done that, we have all of our potential energies, and we're going to bring those over into this sheet here. So we want the potential energies in those cells. To do this, we're going to highlight the data. I'll start with brass. I'll hit Control C. And then what we need to do is we need to just paste the values here, not the math. So if we just hit Control V, it's going to paste the equation. And that's not what we want to do. We want to paste just the values. So using either right click on some of your computers or tapping the touchpad with 2 fingers, we want to bring up this menu, and then we want to paste the values. So if we paste just the values, that's going to give us just the numbers. So I'm going to do that for all 3 of these. Right click or double tap, paste values, and then we're going to paste these values as well. So we'll just copy and we'll paste these here. Okay, very good. So the next thing we need to do is we need to calculate the pendulum velocity. So this is going to be the velocity that the pendulum had after it caught the ball. So the equation we're going to want to use for that is this one right here. So the conservation of energy statement is that the potential energy that the pendulum gains is equal to the kinetic energy that it started with. So we already have the potential energy numbers, so we'll just leave that as PE. And then that's going to equal 1/2 mv squared. So the mass here is the mass of the pendulum and the ball, and we want to solve for velocity. So in order to tell Excel that we want to do some math, we have to type in exactly the formula that will calculate the velocity. So we'll do a quick derivation to determine what that formula should be. First, we get rid of the 1/2 by multiplying by 2, then we divide by m, and then finally we take the square root. So the formula we need to type in to get that math is the square root of 2 times the potential energy over the mass. The way that we can do this is with these formulas here. So this is how we're going to type our math in. First, what this is going to do is it's going to multiply the potential energy by 2, then divide it by the mass, and then these parentheses will tell us that it wants us to, we'll tell Excel we want it to do this math first. Then we use the caret function, so the caret symbol, this little arrow, that tells Excel you want to do a power, and then the equivalent of a square root as a power is 1/2. So 1/2 is the same thing as, so power 1/2 is the same thing as doing a square root. So we'll type this math in here so that we can make Excel do that. So we'll hit equals, then 2 parentheses, 2 times the potential energy, close the parentheses, divided by the mass, 43.5, close that again, caret, parentheses, 1/2, and then we hit enter. And that will get us the velocity of the pendulum. So equals, parentheses, 2 times the potential energy, close, divided by, this is 43.3, close, caret, parentheses, 1/2, close, enter. And then we're going to bring that down. And then one more time. So equals, parentheses, 2 times the potential energy, close, divided by, this one is 37.8, close again, caret, parentheses, 1/2, close, enter there. So, and we'll bring that down as well. So there's our velocities of our pendulums. Now, in order to calculate the spring constant of the spring, we need to know what the kinetic energy of the ball was before it collided with the pendulum. This is actually going to be a conservation of momentum equation. So if we go down here, the initial momentum of the ball is going to be equal to the final momentum of the pendulum and the ball. So the reason that we have to do this is we can't actually just use the kinetic energy of the pendulum to equal the spring energy in the spring launcher, because when the ball goes into the pendulum, there is some energy lost. So we actually have to calculate the velocity of the ball to get the kinetic energy of the ball. So we start with m ball v ball equals m pendulum v pendulum. Then if we divide by the mass of the ball, that's going to get us the velocity of the ball. So mass of the pendulum times its velocity equals the mass of the ball. So mass of the pendulum times the velocity of the pendulum divided by the mass of the ball gets us the velocity of the ball. So to type that in, we do the mass of the pendulum times its velocity divided by the mass of the ball. So those are the 3 equations we're going to use here. So to do that, I went ahead and I made some other equations here. So I took already the velocity of each ball. So I went to my ball, okay. So I got ahead of myself. To do this, we need to calculate the ball velocity. So that's going to be in this sheet, and that's going to be equals the velocity, the mass of the pendulum, 43.5, times the pendulum's velocity divided by the mass of the ball, 8.5, and then that's going to get me my ball velocity. So just as a note, this is in millimeters per second, so don't get too twisted about the fact that it's a pretty large number. And then this is divided by 8.3, and that gets us that. And then same thing over here, this is 37.8 times the pendulum's velocity divided by 2.8, which is the mass of the ball. and that's going to get us our ball velocities. So now that we have the ball velocities, I went ahead and already copied those pieces of data into here. So here are all my ball velocities. The last thing we have to do is calculate the kinetic energy of each shot. So that is going to be, where did I put it? Over here. So the kinetic energy of each shot is going to be 1/2 mv squared, which, did I even put that in here? I may not have. So we want to do 1/2 mv squared for each ball. So we do, here we go, 1/2 times the mass, which is going to be, in this case, 8.5, times the velocity squared. So we'll click that for the velocity and then do power of 2. So 1/2 times the mass times the velocity squared gets us our kinetic energies. So we'll drag that down and then equals, I'll do 1/2 times, this is 8.3 times, parentheses, the velocity, power of 2, hit enter, and then we're going to bring those down. And then finally we do equals 1/2 times the ball mass, 2.8, times the velocity to the power of 2, hit enter, and bring those down as well. So there are our kinetic energies. So we've done all the math that's necessary here. And from this, we're going to carry over our kinetic energy numbers into the last sheet. And those are going to go here. So brass kinetic energy, steel, and aluminum. And so that's what I'm going to do. I'm going to copy, and then once again, I'm going to right click or double tap, paste just the values. For the steel kinetic energy, I'm going to do the same thing. And then we're going to go ahead and paste that. And then for the aluminum kinetic energies, one more time, we do a copy and we paste just the values. And that is what's going to get us our final table. Now, the way that we're going to set up our graph, I'll go back over here. The equation that we're going to, the conservation of energy equation that governs this part is the potential energy of the spring initial equals the final kinetic energy of the ball. So I want a graph that's going to give me a slope that is 1/2 of the spring constant. So the first thing I did was set up my conservation of energy equation, and then the format that this needs to be in is y equals mx plus b. I'm just going to switch around the kinetic energy and potential energy of the spring. So the spring potential energy is calculated by 1/2 kx squared. So if we set this up against y equals mx, this is called linearization, and it's basically just choosing what numbers you want to be your x numbers and what numbers you want to be your y numbers. Go away, malwarebytes. So if we line up y with the kinetic energy, that will put our kinetic energy numbers as our y values, and then malwarebytes, go away. Then for our x values, we're actually going to use x squared, where x in that case is the compression distance. And then we have 1/2 k will be equal to our slope m. So by setting up our x values as x squared, and then using our kinetic energy values as our y's, that's going to give us a graph that looks exactly like this. X squared on the x-axis, ke on the y-axis, with a slope of 1/2 k. And lucky for you, I already did this. So you're going to want to actually have the x squared up in this column here, or this row. And what I did here was I took the compression distances in millimeters and squared them. So you may have slightly different numbers, but it should have been around 10 millimeters, 20 millimeters, and 30 millimeters. So those numbers squared, you're going to have 5 of the same value, so 100, 400, and 900. To make the graph, we highlight all of this data, and what Excel will do is it'll take the first column as the x values, and then each of the 3 kinetic energy columns as a different set of y values. So to get the graph, we go to Insert, we go to Charts up here, and then we're going to choose a standard scatter plot, and that's going to get us our graph. So we can do this. We can change our chart title, and that's going to be kinetic energy versus x squared. And then some other things we're going to want to do are we're going to want some axis titles. I don't know where that menu went. Oh, it's over here. So we want axis titles. And then this one is going to be x squared. And this is going to be, let's see if I can get my mouse in the right place. This is going to be kinetic energy. And then this is, so I'm not 100% sure why this is doing this. You have your two sphere, your brass and your steel basically following the same line, but the aluminum one not. So don't worry too much about that. I'm going to go ahead and, on my own time, figure out why it's doing this. But all we need to do now is get our trend lines. So we're going to click trend line, and we're going to have to do this 3 times. So we'll start with the brass one, and then we're going to do a trend line. Let's see if I click on the orange points. We could do a trend line for that. And then, okay, yeah, we can just click on the points. You can click on the blue dot, get us one for that, and then click on the aluminum one and get a line for that. So the last thing we're going to need to do is actually get the equation. So if we click on the blue dots again, oh, that's an orange dot. Click on the blue dots, go to this little arrow over here, and we want more options. We're going to set the intercept to 0, 0, and then display the equation on the chart. And so that gives us one equation here. Then we do that for the orange points. We go back to the menu, more options on our trend line, set the intercept and display the equation on the chart. And that gives us another one. And then we'll do the same for the aluminum one. Again, I'm not 100% sure why it's doing this. It should, theoretically, be the same. They should all fall in the same line. Again, that's something for me to figure out, not for you. So set intercept display equation, and then that will give us another value here. So these are, if we look back at our kind of setup here, these values are 1/2 K. So all we're going to do now is we're just going to average these because that's the best we can do, and then multiply by 2, and that's going to get us our final value. So if I take my handy dandy calculator out, I do 184 plus 162 plus that rounds up to 61, enter, and then divide that by 3. That's our average slope. And then we wrap that up by multiplying by 2. And that gives us a roundabout number for our spring constant. So for this particular set of data, it would be 271. And then the units on that are newtons per millimeter. So that is going to be your kind of final answer. So if you follow all these steps and get your spring constant, you can wrap up the lab. And that'll be that. So you'll hand in the paper whenever you're done with it. So for one of the classes today, that'll be at the end of class. And then for the other section, you'll have to consider that part of your shop week homework. And you'll turn that in when we see each other again. So hopefully this was helpful. Feel free to go back through the video and revisit all the calculations and how to make the graph and get all the information out of there. So good luck, and yeah, good luck. And we'll stop.